Hello students, welcome to this module 11 on our series of lectures on linear algebra, which is part of the course CG 641 at IIT Kanpur. Until the last couple of modules, we had discussed a very important topic, namely similarity transforms and leading up to diagonalization of matrices. Okay, just a couple of minutes of recap. If I have a linear operator is an abstract object which, when expressed in a n-dimensional space, in a given n-dimensional basis, takes the form of a matrix. Okay, of an n by n matrix. Of course, it is often customary to just say that to represent or call the linear operator A as the matrix A, but remember that this matrix is merely a representation of this object in a given basis. Okay, much as suppose I have a vector, let's say a velocity vector, and this represents, let's say, the velocity of fluid at a point, then you might say that the velocity vector is some 3i plus 4j or something like that, minus 5k. Okay, so the velocity vector is either represented in terms of this form, or you may simply say 3, 4, minus 5 as being the components of this velocity vector in a given basis. Okay, but this is itself not the vector, because this is the representation of the vector in a basis. Of course, these numbers will change. If I go to some other basis, it may become 5, minus 3, 2, or whatever, right, in a different basis. So we cannot say a vector V as just an array of numbers. It is much more than that. In the same way, a linear operator A is also not just the matrix, but the linear operator takes the form of a matrix in a given n-dimensional basis. Okay, this has been something that I have told, explained a few times. Now, this operator, when you represent in a given basis, takes the form of a matrix A. If I change basis, then I told that S inverse AS is A prime, where S is the transformation matrix. It contains the information about how the basis vectors in the new basis are related to the basis vectors in the old basis. This is something that we saw in the last lecture. So if I change the basis, a linear operator changes or transforms in this fashion, and such a transformation is called a similarity transformation. Okay. Now, so in general, A prime, the transform matrix, is S inverse AS. Will be some other matrix, but we ask the question, is there a special transformation, or is there a special basis wherein A prime, the transform matrix, will be purely diagonal? Okay, everywhere else 0 and entries only in the diagonal. Okay, and the answer turned out to be that if you transform a given matrix or express a given matrix in its own eigenvector basis, then A prime will be then, wherein S now becomes the bunch of eigenvectors. Let's say the eigenvalue problem for A is A EI is lambda I EI. Let EI's be the eigenvectors. Let's assume them to be orthonormal. So if I construct a matrix with E's E1 up to En being the vectors that form the first column, second column, and so on up to nth column, where these are the eigenvectors of the matrix, then A prime will become S inverse A S. Okay, and that is nothing but, we found that this turned out to be lambda, where lambda is simply lambda 1 0 0 0, lambda 2 0 0 0, lambda 3, and so on. That is, it will have only the eigenvalues along the diagonal and zeros elsewhere. Okay, this is called uh, this is termed as diagonalization of a matrix. Okay. Now the point is, this all works when you have a set of orthogonal eigenvectors. Okay, and these are guaranteed when you have the underlying matrix to be a Hermitian matrix. Okay, now we will try to generalize these notions to matrices that are not necessarily Hermitian, and wherein you need not necessarily have orthogonal eigenvectors. So that is the objective of the present module. Okay, so let's start from the beginning. If I have a vector, so let me put a topic: generalization to cases where the eigenvectors are not orthogonal. Okay, so let's first start from the very beginning. You have sorry about this. Let's say you have a vector x belonging to the real space Rn. It's an n-dimensional space. Then it can always be represented in terms of the fundamental basis vectors xi, ei, where ei's are such that you have 1 in the ith notation, ith row, and zeros elsewhere. Okay, this is the fundamental basis vector. Okay, this is the fundamental basis vector. So you have e1 up to en. This is an n-dimensional basis. It's an orthonormal basis. So this is ei operating ej is nothing but the inner product ei dagger ej is delta ij. You can verify this very easily. Okay, this is one of the simplest bases that you can think of. Okay, now you can also go to other bases. Take another linearly independent basis, not necessarily orthonormal or orthogonal. Okay, let's call that set x1 xn. Okay, so any vector x can be represented in terms of this basis in the usual manner, I is equal to 1 to n. So I can also write this as this vector x as being represented as these are the coefficients of expansion. There are n such coefficients. So I can write this as a matrix capital X times the coefficient vector alpha, where alpha is just the column vector containing all these coefficients. Okay, these are the coefficients, right? Alpha is just the column vector containing all these coefficients. Okay, and what is x? X is nothing but the matrix comprising of all the n basis vectors in each of its columns. The first column is the first basis vector, and the nth column is the nth basis vector. Because xi's are linearly independent, okay, x inverse exists. Okay, you can invert this matrix capital X. Therefore, if I ask the question, how do I find the coefficients alpha of the vector x in a given basis? You have to take the inversion. So what do? You multiply x inverse dot x, that becomes alpha. Okay, this is the usual way of finding the coefficients of expansion in a given not necessarily orthogonal basis. Okay, now if xi's are orthogonal or orthonormal, then you have xi dagger xj is delta ij. Okay, then the coefficients can be found. Suppose I then have x summation alpha I xi, I going from 1 to n, then the coefficients can be found by orthonormality. Gives the coefficients alpha I. It's very simple because you can simply find xj dagger x is nothing but summation I alpha I xj dagger xi, but this is delta ji, so this will give me summation I alpha I delta ij, which is nothing but alpha j is xj dagger operating on x. Okay, so this is how one finds the coefficient of expansion if the basis is orthonormal. Okay, this luxury is not there if the basis is just linearly independent. Okay, it's not as simple. Okay, so there is one small concept that I would like to introduce in this context. Suppose x is summation alpha I xi. Okay, we can also write this as summation xi alpha I. Alpha i's are scalars, so the order in which it appears doesn't matter. This is summation I xi. Instead of alpha I, I'm going to write this as, what is alpha I? This is xj vector, eigenvector operating on basis vector operating on x. So I can write this as, now because it is alpha j, it is xjx, alpha I is xi x. Okay, or in matrix terms this can be written as xi dagger x. So you have an equation, x is summation I xi dagger x. Okay, now therefore if x is something else times the same vector, that something else should be a matrix, an identity matrix, right? So if I have a set of orthogonal basis vectors, right, then the identity matrix is given by xi dagger. If this basis is complete, right, then this must satisfy this particular representation. This is called, in linear algebra, this is called resolution of identity. This is called resolution of identity. If I have a set of n orthogonal or orthonormal basis vectors, then they must satisfy, if they are a complete basis, they must satisfy xi dagger. Okay, now let's now worry about what if the basis is not orthogonal or orthonormal. What if the basis is not orthonormal? Then of course we can still write some x as summation alpha I times xi, I going from 1 to n, but the coefficients alpha I cannot be found easily because orthonormality doesn't work, right? Now in this context we already introduced a notion of what is called a reciprocal basis. What is a reciprocal basis? You construct a basis, find a basis comprising of vectors z1 to zn, which is related to the original basis x1 xn, such that if I take the inner product of the ith reciprocal basis vector with the jth basis vector of the original basis, then I will get delta ij. That is the first reciprocal vector. If I dot it with the first original basis vector, then they will give the same answer. All the others are orthogonal. Okay, so this is the way reciprocal basis vectors are defined. So this is the definition of reciprocal basis vector. Then the determination of the coefficients of expansion of any vector x in terms of a non-orthogonal basis becomes simple, because I can, how do I find alpha j? I can multiply both sides by j dagger, which is I is equal to 1 to n alpha I zj dagger xi, and this is nothing but delta ij. So this implies that alpha I delta ij is alpha j, so alpha j is zj dagger x. Okay, this is how one computes the coefficients if you have a non-orthogonal basis, but you must construct the reciprocal basis first, and then the calculation of the coefficients becomes as simple as if you had an orthogonal basis or orthonormal basis. Okay, so this is the advantage of reciprocal basis. Okay, so this is called the reciprocal basis. Okay, now x is summation alpha I xi. Yes, and I can again write this as xi alpha I. This is nothing but xi. Instead of alpha I will write zi dagger x. So x is some matrix times itself, so that matrix should be identity. So this is the resolution of identity in a non-orthogonal basis set. What is it? It's simply that summation xi zi dagger I equals 1 to n is the identity matrix. This again tells you that the original basis and the reciprocal basis form a complete set. Okay, now how do I find the reciprocal basis? Or okay, now that this is the resolution of identity if you had a reciprocal basis, now how do you identify the reciprocal basis? Well, we can do that. Let's first collect the original basis in the form of a matrix, wherein take each of the original basis vector and arrange in a column, arrange as the first column, second column, so on, and this collection of columns becomes a matrix. That big matrix is called capital X. Okay, because xi's are linearly independent, that means that x inverse exists. Okay, so we had seen this before. So x inverse times x is equal to identity. Okay, now let's call this as z dagger. Z dagger times x is identity, or so z dagger is identified as x inverse, or z is x inverse whole dagger. Okay, and this z is a matrix. It can be thought to be comprised of n vectors arranged in column. Okay, and those are the reciprocal vectors. Okay, how do we show that? Well, z dagger, z is simply this. So z dagger is the column vector with the Hermitian. So z dagger is this. Z dagger is nothing but x inverse. That's the definition. That's how we identified. Okay, so z dagger times x is nothing but x inverse or x inverse, because I post multiply by x is identity. Okay, so now what is z dagger? Z dagger is this column vectors arranged. So see, these vectors arranged in a column. And what is the matrix X? It is simply x1, and we now know that this is I. That means that if I do the matrix multiplication, this says that z1 dagger x1 is 1. Okay, so this matrix will have components z1 dagger x1, z1 dagger x2, z1 dagger xn, and so on. This is z2 dagger x1, z2 dagger x2, and so on. And this is identity. That means that we have shown that zi xj is delta ij, or in matrix form zi dagger xj is delta ij. Or what we are showing is that the reciprocal vectors are orthonormal to the original basis vectors. The first reciprocal vector is along the same direction as the first basis vector. All the other reciprocal vectors are perpendicular, and so on. Okay. Now the question next happens is how do you find a set of linearly independent eigenvectors? Okay, not orthogonal but just linearly independent. Now here we have to define. So far we had seen Hermitian matrix, symmetric matrix, unitary matrix, orthogonal matrix, and so on, right? Now we are going to define a new term, a new class of matrices called perfect matrices. Perfect matrices are those matrices, by definition, they have n linearly independent eigenvectors. Okay, so perfect matrices may include symmetric matrices, Hermitian matrices, but these are a more general class of matrices. Okay, so they have n linearly independent eigenvectors such that if A is a perfect matrix, AXI is lambda I xi, where I is 1 to n in an n-dimensional space. Okay, and we already know that if I have a bunch of n linearly independent eigenvectors, the resolution of identity with the help of reciprocal vectors is like this, right? So if I operate both sides with A, so this is nothing but AXI ZI dagger. Now AXI is nothing but lambda I xi ZI dagger. Okay, so this is called, and A times I is simply A. This is called the spectral resolution of a matrix this is the spectral resolution of a matrix in terms of its reciprocal and basis and original basis. Okay, this is a spectral resolution of a perfect matrix. A perfect matrix, as we just saw, is a matrix with n linearly independent eigenvectors. Now I'm going to take the adjoint of A here, so A dagger remember that adjoint matrix is the same as its Hermitian conjugate. So A dagger is summation I lambda I star Zi xi dagger. Okay, now if I operate with A dagger, Zj is summation I lambda I star Zi xi dagger Zj. Okay, but this is delta ij. That's how we have constructed the reciprocal basis, right? The reciprocal basis was constructed such that they are orthogonal to the original basis. So this is nothing but A dagger Zj is, this delta function will kill this summation to give rise to, and I will become j lambda j star Zj. So what does this look like? This looks like an eigenvalue problem for A dagger. This is indeed an eigenvalue problem for the adjoint or Hermitian conjugate of A. So what we have shown is that if A is a perfect matrix, with eigenvalues lambda i's, then the eigenvalues of its adjoint, which is A dagger, the Hermitian conjugate, are complex conjugates. This is lambda star, which is a complex conjugate of the eigenvalues of A. Then the eigenvectors of A dagger are the reciprocal vectors of the eigenvectors of A. Okay. So if you have a perfect matrix which has only n linearly independent eigenvectors, sorry, how do I get the reciprocal basis? Let that matrix be A. Solve the eigenvalue problem for its Hermitian conjugate, and the eigenvectors collection, okay, will form the reciprocal basis. Okay, right. So likewise, we also have A is the spectral resolution lambda I xi zi dagger, and the resolution of identity I is nothing but summation I xi zi dagger. Okay, this is the spectral resolution of A. This is resolution of identity. Okay. All right. Now, what is the advantage again of all this? Right. So far, we have been thinking about the properties of Hermitian matrices. Even if you have a perfect matrix, if I have dx dt is Ax, okay, with this a set of coupled ordinary differential equations. Okay. Now, if you want to solve this formally, right, what you can do is the following. A is, let's take a step back, we just showed xi. Now A squared is A into A, so Axi is lambda xi, so this becomes lambda I squared xi zi dagger. So similarly, A to the power any positive integer k is summation lambda I k, right, times xi dagger, right. So if I have a function of A, you can Taylor expand it just like you Taylor expand a real variable. So exponential of a matrix, say t times A, is nothing but summation k equal to 0 to infinity t A whole to the k by k factorial. This is nothing but summation k, right, tk lambda I to the power k, okay, by k factorial times xi. I am substituting the formula for A to the power k here, times xi zi dagger. Okay. Now, okay, of course I have to put double summations here, because there is a summation over I. Okay. If I interchange the two, then exponential of ta is nothing but summation I equal to 1 to n k equal to 0 to infinity t to the k lambda I to the k by k factorial, operating on xi zi dagger. Now this object is nothing but this is like a real e to the t lambda I. This is the Taylor expansion of that, this whole thing, right. So I can write this as exponential of t times the matrix A is summation I is equal to 1 to n exponential of t lambda I times xi Zi dagger. Okay, and this is not true for exponential. Any function of a can be written as f of lambda I xi z dagger. Xi's are the eigenvectors of the original matrix, and zi daggers or the zi's are the eigenvectors of the adjoint or Hermitian conjugate matrix. Okay, so if I had dx dt is a times x, then and x of t equal to 0 is x0 is the initial condition. This is a collection of couple linear differential equations, linear ODEs. Okay, if a is perfect, okay, then the formal solution can be written as x of t is exponential of ta operating on x naught. Okay, this is nothing but summation I equal to 1 to n exponential of t lambda I xi x naught. Okay, we say that the original basis and the reciprocal basis form a biorthogonal set. Okay, now you can also show further that you can also diagonalize a perfect matrix using the same idea. X inverse Ax is equal to lambda. This is a purely diagonal matrix with eigenvalues along the diagonal. Okay, that's the same idea. Okay, now there are some special matrices which we saw in the last lecture, right? You had a normal matrix which is a dagger a dagger is a dagger a. Okay, and this subsumes all the orthogonal, unitary, symmetric and Hermitian. This subsumes all these other special matrices. For normal matrices, okay, you are bound to get an orthogonal eigenbasis, right? Because that's a definition of a normal matrix. Sorry, a normal matrix is supposed to have a set of linearly independent vectors. Okay, and if that happens to be a set of orthogonal eigenvectors, then x dagger ixj is delta ij. Then if it's orthogonal basis, then x inverse Ax is lambda. Okay, so for a normal matrix A, it can be and then you can also show that x transpose or x dagger is x inverse. So this is called an orthogonal or unitary transformation. If it is a real numbered matrix, it's called an orthogonal transformation. Otherwise, it's called a unitary transformation. Okay, so one last definition of a matrix, and this is called a positive definite matrix. What are positive definite matrices? You take a matrix and then pre and post multiply by arbitrary vectors. Okay, so a positive definite matrix is such that this combination, this quadratic form, is always positive for any x, any vector x. Okay, so rho is a real scalar quantity because it's positive, and it's scalar because it's just a number. Okay, so rho is the same as rho star, it's real. That means that x dagger Ax is the same as x dagger A dagger x. Okay, or A is equal to A dagger. If a matrix is positive definite such that it obeys this, then it is also Hermitian. Note that all positive definite matrices are Hermitian, but the other way around is not true. Okay, the not all Hermitian matrices are positive definite. Okay, so you can write for positive definite matrices, X is summation alpha I xi. Now let xi be the eigenvectors of A, of A being positive definite, right? Then rho is nothing but summation I summation j. Okay, remember rho is nothing but x tilde a x dagger ax. Okay, right, and I'm going to substitute for one of the x's this for both the x's this series expansion. Therefore I'll get the double summation and alpha I star xi dagger a. I'm trying to just do this, x dagger ax times a times, okay, and rearranging I'll get summation I summation j alpha I star alpha j a. Okay, now ax I is lambda xi or axj is lambda xj, so this becomes lambda j xi dagger xj. Okay, now xi dagger xj, if it is orthogonal, right, xi dagger xj, of course because all positive definite matrices are Hermitian, so this will be orthogonal. This is nothing but delta ij, and it will kill one of the summations in the double sum, so rho becomes summation I alpha, both I and j will become the same, so j will be I, alpha I star alpha I is the modulus of that the whole square times lambda I. Okay, so because the vectors are arbitrary, then rho is greater than 0 if and only if all the lambdas are greater than 0. This is the definition of positive definite matrices. Okay, now finally we can categorize various types of matrices in the following way. Okay, first the outermost circle okay, and then let me draw a few circles. Not necessarily circles, regions or domains. Just give me a minute while I draw this. Just one more. Okay, now in the class of matrices that we have discussed, the most general matrix is an imperfect matrix. We cannot say anything about its eigenvalues or eigenvectors. Then the next important subclass is perfect matrices, because they at least have perfect matrices have n linearly independent eigenvectors. Then you have normal matrices. Okay, so if you remember, perfect matrices only have n linearly independent eigenvectors. Normal matrices have n orthogonal, the eigenvectors corresponding to distinct eigenvalues are orthogonal. Then you have self-adjoint or Hermitian, where it's not just the eigenvectors are orthogonal, the eigenvalues are real. And then positive definite matrices, PD refers for positive definite. And on the other side you also have unitary matrices, and then orthogonal matrices. Okay, they are also normal matrices, but they need not be necessarily self-adjoint. Okay, now all this will finally, there is one of the simplest possible matrices is finally they will, that is nothing but the identity matrix, which is the simplest matrix that you can think of. Okay, so these are the types of matrices. Each, as you go further and further inside, they get more and more special in terms of their properties. Okay, and this is something that this big picture is something that it's worth having when you try to understand the subject of linear algebra. Okay, now one thing that is important with respect to let me just take a new page. With respect to a perfect matrix is that you can construct a similarity, you can also diagonalize a perfect matrix. How do you diagonalize? Again, you have xi are the eigenvectors which are linearly independent. That's the definition of a perfect matrix. Then you have the reciprocal vectors zj. Okay, these are the reciprocal vectors. Together they form a biorthogonal set, right? So xi dagger zj is delta ij. Okay, so what are zi's? We know how to find zi's. They are the eigenvectors of the adjoint problem. Okay, so you can construct the matrix X such that the eigenvectors of the big matrix X such that the eigenvectors of the perfect matrix form the column. Then x inverse Ax is lambda. Okay, this is something where lambda contains only diagonal entries with eigenvalues of A, otherwise it's 0. Okay, now this is the advantage of having a perfect matrix, that you can still diagonalize a perfect matrix. Okay, now okay, so if A is perfect, it can be diagonalized by similarity transformation. If A is perfect, it can be diagonalized by a similarity transformation. Okay, the column vectors of the transformation matrix are the eigenvectors of A. Okay, and the eventual diagonal matrix will have only the eigenvalues of A as entries. Okay, A xi is lambda I xi. So these are the eigenvectors and these are the eigenvalues. Okay, so again, if you have a perfect matrix, therefore you can solve differential equations like this using similarity, using diagonalization, right? You can do the same thing that we did before for orthogonal matrices. So perfect matrices also render some simplifications, allow for some simplifications, right? And you can solve this by using z is equal to x y, where x is the matrix comprising eigenvectors. So when you do this, then you multiply the whole thing by capital X, then you will get dz dt is x a. Instead of y, I'll put x inverse zeta. Now this is purely diagonal, so it renders a lot of simplification while solving systems of ordinary differential equations. So perfect matrices are also in that sense very special. Okay, now finally, unitary and orthogonal matrices. Okay, so all perfect matrices are diagonalized by a similarity transform. We just showed this. Unitary and orthogonal matrices are somewhat special form of they are all classes of normal matrices. Normal matrices are ones in which A dagger is A dagger A. These are unitary and orthogonal matrices are special cases of a normal matrix. What are unitary and orthogonal matrices? Suppose I take a vector. If A is a unitary matrix, right, then if I transform it, okay, then you can show that the norm of the vector remains the same. The length of the vector does not get altered. Why? Because this is nothing but ax the whole dagger ax. This is nothing but x dagger ax. But A dagger unitary matrix is such that A dagger is equal to A inverse. So this means that this is identity. So this is the original norm is the same as the norm after operating upon by, because this identity, this is also x squared. So we have shown that unitary or orthogonal transformations, they preserve lengths of a vector even after transforming. The length of the vector does not change. Okay, so A dagger A is identity for a unitary matrix. Okay, or you can further say, make a requirement that what is that property that must be satisfied by a matrix such that the lengths are preserved. Then you will find that A dagger must be equal to A inverse, or A dagger A is identity, okay, for a unitary matrix. This is a unitary matrix, right? So what is A dagger A? A dagger, let A be represented as a bunch of column vectors, then A dagger will be A1 dagger, A_n dagger. We know that A dagger A is, or A dagger A is identity. What is A dagger A? It is nothing but A1 dagger multiplied by, this is identity. This means that you can show that AI Aj is delta Ij. That is, the column vectors of a unitary matrix form an orthonormal set. Because this multiplied by this is identity, so this is a matrix comprising of elements like this: A1 dagger A1, A1 dagger A2, A1 dagger AN, A2 dagger A1, A2 dagger A2, A2 dagger AN. This is identity. That means that the column vectors are orthogonal. This is identity, because we know that this has to be identity. So the column vectors of a unitary matrix form an orthogonal set. Okay. Now the real counterpart of unitary is called an orthogonal matrix. Instead of complex conjugates, you have an orthogonal matrix. Okay, and apart from unitary matrices, we also saw Hermitian or self-adjoint matrices, and they are also subclasses of perfect matrices. They are they have real eigenvalues and orthogonal eigenvectors, eigenvalues corresponding to distinct eigenvalues are orthogonal. And the last subclass is a positive definite matrix, wherein you have it's a subclass of Hermitian matrices. If I have x dagger a x, this is always greater than 0. Okay, and you can show that this is nothing but a positive definite matrix. Okay, is a subclass of a Hermitian matrix, and this is true only when all the eigenvalues of A are positive. How do we show that? So we show that through expansion. We say that let A xi is lambda I xi be the eigenvalue problem of this matrix A, which is a positive definite matrix. Okay, what are the conditions? So this means that summation I j alpha I star x I dagger A x j alpha j. Okay, now this is nothing but rho is equal to summation I summation j alpha I star alpha j lambda j xi dagger xj. Now xi dagger xj is nothing but delta ij, because it is a Hermitian matrix, so they have orthogonal eigenvectors. So this means that this will kill one of the sum, so rho will become alpha I squared lambda I. So if rho is greater than 0 for positive definite matrix, that means that all the lambda i's must be greater than 0. So positive definite matrix is a subclass of Hermitian or self-adjoint matrices with all eigenvalues being positive. Okay, this is one of the most special types of matrices. Okay, and then finally we will again refer you to this big picture that we drew for matrices, and we will end with this, and the next module we will start with a system of linear equations, solvability, when are they solvable, when is there a unique solution, and so on. This you would have seen in earlier courses or earlier undergraduate courses, but we will try to place those results in the context of linear algebra principles that we have discussed so far. So this is the most important take-home message at the end of linear algebra modules in terms of properties of matrices. Okay, you have imperfect matrices. Okay, this is just definition. This doesn't belong to. So you have imperfect matrices, then you have a class of perfect matrices which have linearly independent eigenvectors. Then you have normal matrices which have orthogonal eigenvectors. Then you have self-adjoint matrices which have orthogonal eigenvectors and real eigenvalues. Then you have positive definite matrices which have orthogonal eigenvectors, real eigenvalues that are positive. And then on the other side you have unitary and orthogonal matrices. All of them will finally join at the simplest possible matrix, which is the identity matrix. So I'll stop here, and we will continue in the next module with linear equations.